Yesterday, we have discussed regarding gate delays. So, whenever we are going to consider any practical device, we will be having its own delay. So, in such case, so what we have to do is we have to mention the rise time delay, fall time delay, as well as turn off delay. So, whenever we are going to consider rise time, it indicates that from any other state, it has to make a transition for logic high. So it is known as rise time delay. And similarly, from any other state, it has to make a transition to logic zero. That is known as fall time delay. So in such case, what we have to do is we have to mention at least how much time it has to take to make the transition, because as soon as we give the input, immediately the device has to process and then it has to give the output. So we need that time. So that is why we are going to consider it as rise time, fall time. And similarly, whenever the device is made inactive, in that case it has to turn off. So that is why we are going to use turn off delay. And while mentioning the delay, either we can mention only one delay or two delays or three delays. So when we mention only one delay, it will be taken as common delay for rise time, fall time, as well as turn off. If I mention two delays, then the first one will be taken as a rise time delay, second one will be the fall time delay, and third one, that is the turn off delay, will be minimum of rise time and fall time delay. And if I mention all the three types of delay, then we can able to get the first one as rise time delay, second one as fall time, and the third one as turn off delay. So like this we can able to mention the delays. If we do not mention any delays, then what it indicates, the default delay is 0, and this we can achieve in simulator but not in the practical device. So whenever we are writing a program, we should keep in mind that we are writing program for the practical hardware device. So that is why we have to consider delays. Okay. And these are some of the examples we have discussed. And next what we are going to consider is minimum delay, typical delay, and maximum delay. Because when we are writing program using these delays, we will not be knowing for which implementation technology we are writing the program. So it can be the same program can holds good for all the types of technology. So that is why will not be as we are not sure about what is the exact gate delay for a particular technology, we are going to mention a range of delays. So a range of delays means, so here min represents at least this much delay it has to take, and maximum represents it should not take the delay beyond this value, and typical delay means on an average. So typically it will going to see when we are going to consider any device, so based on the observation we will going to analyze on an average this much delay it will going to consider. So we can mention the value of typical delay, and then we can able to observe the corresponding output. So now let us consider the, here we can see the minimum delay is the minimum delay value that the designer expects the gate to have, and maximum is the maximum value the designer expects the gate to have, and typical delay indicates that the designer it has to take this much delay. So neither maximum nor minimum. So it indicates that if he know exactly a particular implementation technology, then he can mention the typical value of the delay. And let us see how we can able to achieve this. And also the delay depends upon what type of simulators we are considering and all. So here this is one of the example. If we are consider, or general syntax we can consider, if we are considering only one delay, so in that case what is the minimum delay, what is the maximum delay, and what is the typical delay, that we can mention. So in order to differentiate between minimum, typical, and maximum, we are going to use semicolon, sorry, colon. Here you can observe in this example, I have taken and ash 4:5:6. So this indicates that I am considering only one type of delay. Okay, if I am considering two delays, then the delays has to be separated by comma, because in the previous examples we have observed that whenever we are going to consider more than one delay, we will going to separate the delay using comma. Okay, so that is why in one particular delay, there will be three parts: minimum delay, typical delay, and maximum delay. So here, if I am considering only one type, I can mention like this. And if I consider this type of two delays, so in that case, I have to mention all the three criteria for minimum, typical, and maximum for rise time as well as fall time. So in this example, we can see the minimum delay, rise time delay is 3 for AND gate, and the fall time delay is 5. These are the minimum values. And 4 as well as 6 indicates the typical delay for rise time and fall time. And here 5 and 7 indicates the maximum delay for rise and fall time. So now in this, if I want to consider turn off delay, so now I have to observe minimum rise time delay and minimum fall time delay. So in these two, again I have to find out which is the least one. Since 3 is the least one, to turn off at least it has to take 3 time units of delay. Similarly, when I consider the maximum delays, so in that case the turn off delay will be the minimum of maximum rise time delay and maximum fall time delay. So if we observe in this example, maximum rise time delay is 5 and maximum fall time delay is 7. Minimum of these two is equal to 5. So as a result, the device will turn off with a minimum delay of 5, with a maximum delay of 5 time units. So like this we are going to consider. Remember one thing, while considering the minimum, maximum, and typical delays, whether if we are using two delays, we have to compare minimum value of rise time with minimum value of fall time. Similarly, typical value of rise time with typical value of fall time. So like this we have to compare. So simply we cannot tell among them the minimum is, among this range the minimum is 3 and among this range the minimum is 5. So it cannot take the minimum turn off delay as only 3. Okay, so while comparing we have to check all these things. So as a result, here what will be the range of turn off delay? It will be equal to minimum turn off delay is 3, typical turn off delay is 4, and maximum turn off delay is 5. Okay, so like this we are going to consider. So now let us observe this in an example. So here, so when we are going to consider an example, so first let us consider a module and let it be buffer of 1 bit. So let me don't take only buff. So we can consider it as 1 bit buffer. So why I am considering 1 bit buffer means, so here we are having a control pin so that we can able to turn off the device as well as we can able to activate the device with logic 1 or logic 0. So here I'll take one input port, let I be the input port and O be the output port and C be the control pin. Okay. So now I will define input I, comma C, because control is also an input for buffer and I is also an input for buffer, and output of the buffer is O. Okay, and let us write the program as buff if 1. Okay, so it indicates that I am considering the control logic as 1. Whenever the control logic is equal to 1, in that case it will activate the buffer. Okay, so now according to the syntax, so the first we have to write the output, and then we have to write the input, and last control. Okay, this is the general syntax for buffif, and the next let us consider end module. Okay, so in order to check whether it is working properly or not, so what we have to do, we have to simulate and then we have to check, isn't it? So to simulate, we are going to consider module and let it be stimulus or test bench TB. And next, input ports are declared as registers and output ports are declared as wires. So we will be having input ports as reg and output ports as wire. And next, component instantiation. To instantiate the component, I'll use the ordered list connection. So I'll just copy the module definition and here I'll give an instance name. So I of the module buffif1 will be connected to I of register test bench. So like this, the connection based on the position connection will be done. And next we have to give the initial value. Initial, and when more number of sentences are there, we have to use begin. And here let us consider the value of I is equal to 1 and C is equal to 1. So control is also 1 and I is also 1. According to that, what will be the output? So that we have to check. And similarly, after some delay, because we have to observe the value properly. If I do not give delay, what happens? While giving the input, immediately without delay all the values will be executed and I cannot able to see the difference. Only the final value I can able to see. So that is why we are going to give some delay so that I can able to observe what is the output for the given input. So after some delay, let C is equal to 0. So I am not changing the input I, but I am changing the control input. And again, after some delay, I'll make C is equal to 1. And again, after some delay, let C is equal to 1 bit binary X. Okay. When unknown is the input, what should be the output? That also we should able to see. According to the truth table, we know that when control logic is 1, whatever the input is there, we'll go to get the same output. But when control logic is 0, it will deactivate the buffer. So there the output should be equal to high impedance. And when the value is equal to, when the control value is equal to X, in that case, it will going to give weak strength input. Since the input is 1, it will going to give weak high. And similarly, let us see whether we are going to get weak low. So I will keep control as X only and I'll change the input I to 0. Okay. And next, after some delay, it has to turn off. So dollar finish, and then end in module. Okay. So now we have to select the simulator. So the simulator, see if in your system or in your mobile phone, if this particular simulator is not working, you can select any of the simulator. It doesn't mean that you have to select only this particular simulator. Okay. And next, I'll enable the output waveform. And then have forgotten one thing. I think here we have to consider dollar dump. What is that? Okay, I'll get that in the log box only. Yeah, so this is dollar dump file as well as dollar variables. So now let us run the program. Yeah, so here you can able to see the output. So initially, see, it has executed from 0th second to 50-second. So at 0th second, we had given the input, control input as well as input as 1. So accordingly, we should get the output O. Okay, since the control input is 1, whatever the input is there, the same is there in the output. After 10 seconds of delay, I have changed control input to 0. So here you can observe, wherever I place this cursor, it will show the value present at that particular position. So the output is equal to Z because it has deactivated the device. Even though if the input is high, as the control logic is 0, we are getting the output as Z. And now again after 10 time units, I have changed the value of control input to 1. So whatever the input is there, the same value I am getting here. And after that, we have changed the control input to X. Isn't it? So here, what we are getting is X. So why we are getting the output as X means it has to represent the weak strength. So here it cannot, in this particular simulator or waveform, it cannot represent H or L. So that is why it cannot indicate the the output as weakest value of 0 in terms of waveform. So that is why it has displayed it as X. And similarly, even though if I change the input to 0, there also I am going to get X, as it cannot display the value as weak high as well as weak low. It will going to display only these 4 values, 0, 1, X and Z. So accordingly, it is showing the output as X. Okay, this is how we are going to consider when we are using buffer. So now, why I took this example is, yesterday while discussing, we have considered turn off delay, isn't it? So in this, we had, in this example, we had considered turn off delay that we were not able to observe in case of AND as well as OR gates, NOT and other gates. But here you can able to observe the turn off delay, because as the control changes to 0, it will turn off the device. So that is why to indicate that example, I have taken this buffer. So now let me give the delay as 5. So in that case, yeah, instead of this value, anyway, we know that it will not going to display the weak. So I'll just make the value I is equal to 0. So when control logic is 1, whatever the input is there, the same it has to display. Previously, we have checked the value for 1, and now let us examine for 0. So now when we execute this, here For all the values, it has to take 5 time units of delay. See here, as the input as the input is assigned at 0th second, after 5 time units, we are getting the actual output. Means it has been shifted by 5 seconds. Output waveform has been shifted by 5 seconds. It will going to check the corresponding value at this position. Still the value of C and I is equal to 1. So it will assign the output O is equal to 1. So like this we are going to get the output. Similarly, here also, even though when I change the value of control to control to 0 at 10 seconds, it is changing at 15 seconds. So like this the value has been shifted. And here what we can observe, control is 1 but input is 0. So after 5 seconds the output has been changed to 0. So like this we are going to get the output when I use only one type of delay. So now let me consider 3 delays. Okay, so here the first one is rise delay, next one is fall delay, and the third one is turn off delay. So these values are maximum. Let me take the lesser values. Okay, so now when we run this program, we can able to see whenever there is a transition from logic Z, any other logic to logic high, it will take only 2 time units of delay. And to turn off, what we have mentioned in our program, this is rise delay, fall delay, and for turn off 4 time units. So it has taken, see here the control has made 0 at 10 time units, and after 4 seconds it has changed to Z. So the turn off delay taken is 4. And again here the value of the input is changing from logic high to logic 0. So output has should also change. But here we can observe that it has taken the delay of how much? It has taken the delay of only 3 seconds, because we have mentioned fall time is 3, rise time is 2, and turn off time is 4. Okay, this is how we are going to consider. And now let us consider the range of rise time delay, range of fall time delay, and range of turn off delay. So if I mention only one delay, in that case I can mention the minimum rise delay is 2 and the typical value is 3 and the maximum value is 4. So in that case, here what happens is, since we are running on the simulator, by default it will going to take either minimum or typical value, not the maximum value. It depends on the simulator. Yeah, so this particular simulator, because we are running on the cloud, isn't it, this program? So how much time it will going to take based on the simulator, it will going to select either minimum, typical, or maximum. So here in this simulator, by default it has taken 3 seconds of delay, means typical value it has taken. If I download the same program for the hardware, it may take the delay between 2 to 4. Okay, in the simulator, as I have mentioned the typical value, it has taken the typical values, and common typical value for all the delay, rise time delay, for turn off delay, as well as fall delay. So for all these things it has taken the same time delay. And now if I want to give 2 types of delay, so for rise time the minimum value is 2. So let me consider for fall time the minimum value is 3 and the typical value for fall time is 4 and the typical value, maximum value for fall time is 5. So now what it has to do, since this is a simulator, usually as I have mentioned the typical value, it will going to consider typical values of rise time and fall time delay. Okay, so now let us run this program. Okay. So in this, for rise time, it has taken 3. And here you can see for turn off time, isn't it? So since I have not mentioned 2 delays, I have mentioned only, sorry, I have not mentioned 3 delays. I have mentioned only rise delay as well as fall delay. So turn off will be minimum of rise and fall. So the minimum value of rise time in case of typical values, the minimum value is 3, and for fall time, the typical value is 4. So between 3 and 4, minimum is 3. So to turn off, it has taken 3 time units of delay. Okay, and so yeah, and here for fall time means for making a transition from logic high to logic 0, how much seconds of delay it has taken, here you can observe. And also if you are not able to see here, here you can see the corresponding time where the marker is. So the input is changed at 30 seconds, but the output is changing from high to low is 34 seconds. Means it has taken 4 time units of delay to make a transition. And now in the same thing, if I mention the typical value for turn off time also, then it will take the same values. So let me consider the turn off time a little bit more. I will take the minimum value for turn off is 5 and typical value is 6 and maximum value is 7. So now the first one is rise, fall and turn off. So now let us observe that in order to, since the simulator is taking typical values, so in order to change for logic high, it is 3, change for logic 0, it is 4, and change for high impedance, it is 6. Okay, so let us execute this program and observe the waveform. So here you can observe again the same thing, it has been maintained. Change from any other value to logic high, it has taken 3 seconds of delay. And here change from logic high to logic 0, it has taken 4 seconds of delay. But here you observe change from logic any other state to high impedance, how much time it has taken. Input has changed at 10 seconds, but the output has changed at 16 seconds. So as a result, it has taken the typical turn off time as 6 seconds according to the program, because in this program I have mentioned the typical turn off time as 6. So that is why it has taken the typical turn off time as 6. This is regarding how to use time delays. So why I am explaining all this with so much detail, because in the test or in the exam they may mention the corresponding delays and you are supposed to write program using the delays. And whenever you write program and if stimulus is asked, so you have to write waveform. If stimulus is not asked, stimulus means test bench. So if this program is not asked, in that case you need not necessary to write the output waveform. But when once this particular program stimulus for the design is asked, in that case according to the given input you are supposed to write the output waveform. Like how we are getting the waveform here, in the same way. See, if they ask to write a buffer with those particular delays, program for buffer with those particular delays, in that case you have to write that program and then you have to write the stimulus and then you have to write the waveform, so that you'll come to know which, they'll come to know whether you have understood the question properly and you have written the answer correctly. So that is why waveform will convey more information rather than the other explanation. So that is why whenever you write any program, if they ask you to write test bench or stimulus program, after writing the stimulus program, it's better to write the waveform. So while writing the waveform, you should be very careful. You should know what delays you have taken and how much delay you have to mention in the output waveform. Okay. So according to that, we have to write. So now in this, we have discussed delays and different range of delays. And the next one, this is the example. Okay. So I think all of you can open EDA playground in your phone or in your laptop in which you are seeing attending the class, and you can able to write program for this. See, like this they will going to ask the question. So for this combinational circuit, they have mentioned what are the input and output ports and what is the name of the wire and also how much delay it has to take. So here what they have mentioned, only one delay. Okay. And also they have not mentioned the typical value as well as the range of rise as well as fall time. So that is why we have to consider a common delay for all the gates. And gate, I mean to turn on from other values to logic high, 5 delay, and fall time it will take 5 time units of delay, and to turn off 5 time units of delay. So like this you are going to get. Okay. So now just write program for this, and I'll ask any one of you to share so that you'll come to know whether you're able to write the program and what type of output you are going to get, that also we can able to observe. Okay, as the input changes, we have to analyze, isn't it? So that analysis we have to do. So before that, let me show an example here. If the value of A and B, if these are the initial values, okay. So in that case, what happens? So here we are having A is equal to 1, B is equal to 0, and C is equal to 1. So accordingly, what should be the output of E? E should be equal to 0. And this is a OR gate, isn't it? So it will, the output of the OR gate will be equal to 1. So now let us consider the value of A will remain as it is and B will change from logic 0 to logic 1. When B changes from 0 to 1, the output of AND gate will change from 0 to 1, but output of OR gate will not change. So why the output of OR gate will not change? In OR gate, already one input is high. So whatever may be the value of other input, your output will be always high. So now, if the value of C changes from logic high to logic 0, now also the AND gate, OR gate output will not change because AND gate output is continuously equal to 1. So as a result, OR gate output is 1. And now, if the value of A changes to 0, now what happens? The value of E will change from 1 to 0. So now AND gate output is also 0 and OR gate output is for this C input is also 0. So as a result, the output of OR gate will change to 0. So this we can able to analyze, but how much delay it will going to take, that matters, isn't it? So initially we have assigned 0 and 1. So after 5 time units of delay, so at 0th time, the value of E and the value of out, let us represent this time. Okay, so the value of E will change to 0 at what time? 5 time units. Okay, and the value of output, when it will change? See, since C value is equal to 1, it will not it's need not necessary to wait for this output. Immediately it has to change, isn't it? So accordingly, output will change to 1 at 4 time units of delay. Okay. So now when the value of E will change to 1, so here I am changing the value of B from 0 to high. Let me consider after uh, 10 time units we are changing. Okay. So after 10 time units, the value of B has been changed, means from 10, it will take 5 extra time units. So as a result, it will take at the value will change at 15 time units. Okay. This change has occurred at 10 time units, and this change it has to occur at 0 time unit. This is for B. Okay. So accordingly, the value of E will change at after 5 time units, and value of E here it will change after 15 time units. Now I am changing the value of C from logic high to logic 0. Okay. At what time? Let me consider I am changing this value at time 20 time units. So as a result, what we are going to get? After this 20, still B is equal to 1. So output will not change. Even though the C changes, output will not change. Output is continuously 1. And now the value of A will change to 0 at 30 time units. Okay. So at 30 time units, the value of A will change to 0. So accordingly, when the value of E has to change from 1 to 0, it has to change from 1 to 0 after 5 units. So at 30 A changes means E will change at 35. So when the value of E changes at 35, then the value of OR gate output has to change. So it will take another 4 time units of delay. So at 39 time units, the value of output will change from logic high to logic 0. So this thing we have to observe in our program. So now in this case, if I consider the same, I'll just take this as CKT, that is circuit. So here the output was out and inputs are A, B and C. So accordingly, we are going to write the corresponding ports here. And now, without delay, we cannot consider, right? They have given typical delay. Okay. 5 for AND gate. AND gate, and for AND gate, the output is E and the inputs are A and B. So since E is not a IO port, it is a wire. We have to declare that. And next, for OR gate, we are having a delay of 4. And the corresponding output port of OR gate is out, and input ports are E as well as C. Okay. Yeah. So now let us give the corresponding inputs. What we discussed in the example, let us consider the same values. So now we have done the module instantiation, and the next thing is initially we have taken A is equal to 1, B is equal to 0 and C is equal to 1. Okay. So accordingly here A is 1, B is 0, C is equal to 1. And after 10 time units, B will change from 1 to 0. So after 10 time units, B will change from 0 to 1. Okay. And after this, we should get the output. Then at 20 time units, C has to change. So already 10 time units has been finished. So again, after another 10 time units, C has to change from logic high to logic 0. So now after this, we are changing the value of A from 1 to 0 at 30 time units. So at another, see, initially it is 0, then 10, plus 10 means 20, plus 10 means 30. So here A will change from 1 to 0. And let me consider some maximum delay and terminate. So now we can observe the output. Where is the error? Where it is in test bench SV fifth line. Oh, I have not considered the corresponding port map. Out A, B, C. Yeah. So now, according to our program, here, when the inputs are given A, B and C, here you can observe that E, the value of E is updated at 5 seconds because AND gate output is having a delay of 5 seconds, and you can observe my output is equal to 1 at 4 seconds. So as I discussed in this example, the value of E will change at 5 seconds and the value of output will change at 4 seconds. In the same way, here also the value of E is changed at 5 seconds and out is changed at 4 seconds. And next, we are changing the value of B input. But still the output as well as E is not changing, because for AND gate, when both the inputs are high, output should be high, but it is having a delay of 5 time units. So after 5 time units, it is changing. But OR gate output is not changing because both the inputs or any one inputs is high for the OR gate, then always it will be equal to high only. Then after 20 time units, I am changing the value of C. Since E is high, the output of OR gate is high only. It will not going to change. And now after 30 time units, what we are doing? We are changing the value of A to 0. So when the value of A changes to 0, at 35 time units, E has to change, and at 39 time units, the corresponding output has to change. So accordingly, here we can observe that at 35 time units, the value of E is changed, and at 39 time units, the value of output is changed. So like this, you are supposed to analyze the waveform when you write the program. So before getting the waveform only, we did analysis here, isn't it? In the same way, in exam also, you are supposed to analyze based on the waveform. How much delay we are getting to get the final output.